Welcome to a screencast on electromagnetic energy. Electromagnetic waves are sinusoidal waves that have both an electric and a magnetic component. Here we're showing just one of them. They oscillate up and down, and they're characterized by several things. We often say that electromagnetic waves have an amplitude. That's essentially the height of the wave. They have a distance from one peak to one peak, or one trough to one trough, which is called the wavelength, and it's symbolized by the Greek letter lambda. They have a frequency, which as the wave is moving, if you count how many actual repetitions of the wave go by in a given amount of time, that's the frequency, and it's characterized by the Greek letter nu. And then they travel at a particular speed, and electromagnetic radiation travels at the speed of light, and the speed of light is 2.998 times 10 to the 8th meters per second in a vacuum, and it's symbolized by the letter C. Now, these quantities are related to each other, and specifically the wavelength times the frequency of a given type of electromagnetic radiation equals the speed of light. So lambda times nu equals C is a generally true relationship for electromagnetic radiation. And light or electromagnetic radiation comes in the form of little chunks or pieces, or often called wave packets. The term we use is photons of electromagnetic waves or electromagnetic radiation. And here's a depiction of a photon, generic photon, with numerous oscillations, but it has a start and a stop. It's not continuous, it's actually a chunk of electromagnetic radiation. Here is a photon of red light depicted. Here is a photon of purple light depicted. Notice they both have oscillations, but they have different wavelengths, therefore different frequencies, therefore different energies, and different colors. And the amount of energy a particular photon of a particular type of electromagnetic radiation contains is given by the relationship E equals h nu. So E stands for the energy of a photon, nu is the frequency, which we've just seen, and then h is Planck's constant. It's a constant with the value of 6.626 times 10 to the minus 34th joule seconds. Now, electromagnetic radiation or electromagnetic waves has a huge spectrum from high energy, short wavelength, high frequency gamma radiation through X-rays, ultraviolet, visible, infrared, microwave, and TV and radio waves. And at this end of the spectrum, radio waves and TV waves are very low energy, long wavelength, high frequency. Here are a number of examples of electromagnetic radiation used in your daily life: X-rays, dental curing, night vision goggles, TV remote controls, weather radar, cell phones, etc. And visible light is only a tiny little piece of this. Here is it kind of expanded out. And the electromagnetic spectrum, as it's shown here, has increasing wavelength going from left to right, has increasing frequency going from right to left, and note frequency and wavelength are inversely related or inversely proportional, and then increasing energy also going from right to left, because energy and frequency are directly related and energy and wavelength are inversely related. Okay, and let's do a little bit of calculation practice using these relationships. And the first example is we have a green diode laser light with a wavelength of 532 nanometers. And what's the frequency of this laser light? And we're going to invoke the wavelength frequency relationship, lambda times nu equals C. We know the wavelength. We always know the speed of light, so we'd like to find the frequency. And if we solve this equation for nu, we get nu equals C over lambda. And now we just plug in values. C is 2.998 times 10 to the 8th meters per second. And lambda is 532 nanometers, but we need to convert this to meters, so 532 times 10 to the minus 9th meters, to ensure that our units work out nicely. So we get meters to cancel, and this gives us a value of 5.64 times 10 to the 14th per second. So that's 5.64 times 10 to the 14th oscillations of this wave every second. And it's worth noting that we also use the unit hertz, symbolized by Hz, for per second. So both of these answers would be fine. Okay, now let's take a look at an example where we're looking at a particular radio station that uses electromagnetic waves to carry its signal, and that those waves have a frequency of 89.7 megahertz. And the question is, what's the wavelength of these radio waves? Well, again, we'll invoke that lambda times nu equals c, but this time we know the frequency nu, and we want to find the wavelength lambda. So this time we solve for lambda. Lambda equals c over nu. Plug in the value of c and the value of frequency. And note again to pay attention to units. We're going to convert 89.7 megahertz into hertz. So 89.7 times 10 to the 6th hertz, or 89.7 times 10 to the 6th per second. In this case, the seconds cancel, and we're left with units of meters, and the value is 3.34. So one wave, or the wavelength of this radio station's waves, is the very long 3.34 meters. And let's do one more example. This time let's deal with energy. What's the energy of a photon of the green laser light that we did in a previous example? And note, we were originally given the wavelength of the laser light, and we then calculated the frequency of the laser light. And to find energy, the relationship is energy is related to frequency equals h nu. So we're going to use the frequency here, which we figured out from the wavelength. And when we plug in our values, Planck's constant is 6.626 times 10 to the negative 34th joule seconds. We multiply by the frequency, 5.64 times 10 to the 14th per second. Seconds and per seconds cancel, giving us 3.74 times 10 to the negative 19th joules for the energy of one photon of the green laser light. And one other thing to note, if we hadn't calculated the frequency initially from the wavelength, we could in fact take the wavelength frequency equation and the energy frequency equations and merge them and get the energy equation in terms of just wavelength and solve in one step after that, and you should get the same value by doing it that way. And that is it for an introduction to electromagnetic energy screencast.